Now let's turn around and see what the fourth chapter is. This is solving linear constant coefficient differential equations using D operators. The type of differential equations we looked at when we were in section 3. So the D operator, first in section 4.1, we pay our attention to the D operators. So first let's go through the definition. Here we don't have to have a lengthy definition, but this is just a notation kind of. So d over dx, this is an operator. If you put something, you will get something else. Like for example, if you put x squared, you get 2x. If you put sin x, you get cos x as the answer. So operator means if you put a function in front of that, you will get something else as a result. So you denote this guy by capital D. Now since it is D, its inverse or 1 over D can be taken as integration. So operator theory allows us to work with this very easily and freely. We don't have to worry about very, various conditions and stuff like that when we usually work with algebra. Okay. Now, let's find these things. These are first set of examples. Because when we solve differential equations, you will encounter stuff like this. Okay. Now take this one for example. Now D is the derivative, differentiation, derivative operator. So you break this into two parts like this. D of sin 2x, 2 times D of cos 2x. Since differential operator is linear, you can break this into two, right? Break this into two parts, and at the same time, when you have a constant in front, you can pull it out. Okay. Now this is what you get. Once you encounter this, you can differentiate this. The derivative of this is what? Cos 2x, but you get 2 to the front because the derivative of this is 2. Here 2 times the derivative of this. What is the derivative of this? Minus 2 sin 2x. So that minus 2 multiplied with this 2 will give you minus 4. So that's it. What about this one? This is integration, but don't put the arbitrary constant. So the integral for the entire derivative of this one is 1 over 3 sin 3x. Now let's take this one. Here the function has two components. Here the derivative operator has two components. It's okay. You break this into two parts. D times sin 4x, 3 times sin 4x. So this is the derivative of this. What is it? 4 times cos 4x. So it's a piece of cake. Like A-level stuff, but notation is quite simpler. Let's go for the third one. This is what you have here. So you can break this into three parts like this. Now this means what? The second derivative. D times D means the second derivative. I could have written that there. Let's go there. Also, this means you applied it twice. And so on. If you have D cube, that means what? D3 over dx3. The third derivative of something. So, here you can break this into two parts. This means what? The second derivative. Derivative of the derivative. So break this into two parts and consider this one. Here you know what it is. Derivative. So when you differentiate this, how do you differentiate this? 2 times e to the power 2x. Here you get the same thing. Now if you go further, one step, you have to differentiate this again. So you get another 2 in the front. You get 2 squared. We know that 2 squared is 4, but we will have it like this. So you have this one. Now if you pull out e to the power 2x to the right, what will you get? 2 squared, 4 times 2, here you get 5. Now 2 squared is 4, this is 8, this is 5. Right? They sum up to 17. Now, I did this for some purpose. With some purpose. Look, if you compare these two steps, what can you say? Do you have to go through all those steps again? Look, do you have to go through these steps? Look what happens. When you have d squared, you have 2 squared. When you have 4 times d, you have 4 times 2. You have 5. So what should you do? You can simply plug in 2 for d. That's all. That's what it says. And it is true for anything, any such function of d operators. So that can, you can form, you can come up with the formula once you see this one. What is that formula? If you have a function of d, if you have e to the power alpha x, what you can do is that you can replace d by 2 here. Otherwise, if you have any alpha, you can replace d by alpha. So it is something like this. You can have any function d. What would you get? You can simply plug in alpha here. Don't take this down when you take down notes, but we'll later note this down. So you have any function here, you have e to the power alpha here, alpha x. So you can straight away jump from here to here. Look, you plug in 2 for d. That's all. So let me write that formula there. In fact, we are going to figure out 3 formulas. The first one, we are going to deal with 3 formulas. The first one is this. If you have something like this, you can substitute alpha for d. Right? So that's how you have to do it. It's easy. Now we'll go for one more. In fact, several more, right? Let's have this one now. Here you have d squared. It's a function of d squared. Right? Let's see what happens. Now, okay, you can break this into 2 parts. So d squared means what? The second derivative. So you can write it as d times d. Now, first take care of this one. Deal with this. So the derivative of sine 3x is what? 3 times cos 3x. Now again you have a d. So you differentiate this again. What would you get? You can pull out 3, this 3. When you differentiate cos 3x, you get minus 3 sine 3x. Now combine these two. You get minus 3 squared. Remember, minus 3 squared is not 9. It is minus 9. Why? 3 squared goes first. 9. So it's minus 9. But this is minus 9, right? But if you have this one, this is 9. So the absence of the parenthesis gives you a different value. So this is minus 9. Right? Plus 4. Can you straight away come from here to here? Look, you have sine 3x. You have this in terms of sine 3x. You have 4 here. It's kept intact. But what about this one? D squared is replaced by minus 3 squared. 3 is what? The angle you have here, like the constant you have here. Okay. We'll do one more. We'll later take care of this one. Look at this. Again, it is something like that. So you can break this into 2 parts. You can write this as d times d cos 2x because it's a second derivative. Derivative of the derivative. Now you can take this part. Differentiate. You get minus 2 sine 2x times d. Here you have this one. Now again you differentiate this. When you differentiate this, you can first pull out this minus 2. So you have to differentiate sine 2x. Derivative of sine 2x is 2 cos 2x. So 2 times minus 2, you get this one. Again, look. Can't we jump from there to here? You can do that. Look, cos 2x is there. If you pull out this, I could have pulled out that. Pulled, no? Here you see I have pulled out. But there, I didn't, let me do that for you. This row. Square should come inside. This is minus 4 plus 7, 3. So can't you jump from there to here? Look, 7 is there, cos 2x is there, but what about this one? D squared is replaced by minus 2 squared. It is not minus 2 quantity squared, it is just minus 2 squared. 2 is the number here. So you can again come up with the formula looking at this one and this one. And it's true for anything. This is not an accident. It's true for any such case. So you can write, there are two formulas. Fd times cos bx, fd squared. It should be a function of d squared. Wherever you have d squared, you have put here minus 2 squared. Or if you have, it should be a function of d squared. The reason is this. When you take cosine, when you differentiate 2 times, you get that. Right? Let me show you. Say for example, if you just take this one, cos 3x, what would you get? When you first differentiate, you get minus 3 sine 3x. When you differentiate it again, what would you get? Minus 3 times 3 cos 6. Again, you get once you divide, once you differentiate cos or sine twice, you get the same function back, but you get an additional constant. Sorry. Look, this minus sign is what? Minus 3 squared. 3 is this constant, you plug in it here, but it is not 3 squared, it is minus 3 squared. You have to force a minus sign into that formula. So if you have something like this, instead of d squared, you have to put minus b squared. Not exactly b squared, minus b squared. Similarly, if you have sin bx in the place of cos bx, you have this one. Right? So those are the formulas we have. Proof of them would be a little tedious, but it's beyond our scope. We'll using examples, we'll try to understand this one. That would be enough. Even if fd can be a rational function, that's okay. You can have something beneath the division line, like something over something. You can have it like that, right? Still, it's fine. Now we'll go through this one. Look, you have this. You can probably try this. You break this into 3 parts. Now you can write d to the power 4 like this. Here d squared like this. Then keep this d cube intact, and the derivative of this is 2 cos 2x. Here also the derivative is the same thing. Now you break this one again. d2 times d squared times d. Now the derivative of this function is this. Right, here you simply keep it like that. You know that 7 times 4 is 28, but we'll have it like that for some reason. Now here again you break this into 2 parts. Consider this one. You get another 2. So minus 8 cos 2x. You differentiate again, you get 16 sine. Why 16? Because you get another minus 2. Because it is minus sine 2x times 2. You get another minus 2. That minus 2 combines with this one will give you 16. Now this is what? you can the angle is 2x. So you can write this as minus 2 squared. Here also you can do the same thing. Minus 2 squared is minus 4. If you square it, you get 16. Right? I think I need one more step here. Let me change this. This fine. This one. The most, important step is missing. So if you pull out sine 2x from the right, what would you get? Square of this one. Because square of, this is minus 4. When you square it, you get you get plus 16. Then you have this one. Look, can you come from straight away, come from here to here? If this is not clear, you may write it like this. Now this is, look, this is square of d squared. Square of d squared, right? So when you plug in this guy for d squared, d to the power 4 will be this one. Here 7 times, look, for d squared, this is what you substitute. Here you keep it as it is. So again the same thing, what we went through earlier. So d squared should be replaced by minus b squared. You can straight away jump from here, there to here. So it's easier, right? Now the last one. This is, let's take this product and see what happens. Now you can break this into 2 parts, right? This is how you do it. 4 times 6 times e to the power 3x. Here 5d times this one. Now you differentiate this. This is a product. You keep 5 aside, and derivative of this one is what? Derivative of x times e to the power 3x. Then derivative of this one, 3 times e to the power 3x times x. You keep it as it is. Now you pull out e to the power 3x from this one, from everything. So when you pull this out, you get 5 dx. When you pull this out, you get 3x, but it is multiplied by 5. You get 15x. Now you have this one. Since this is pulled out, you have 4x. Now you can pull out x as well, because x is there in every term. So you pull out x to this side, you get 5d plus 15 plus 4. Here 5 is common. So I write it like this. 5, this is 15, this is 4. Now can you jump from here to here? Yes, you can jump. Why? This is a product of 2 functions, but one is an exponential function, e to the power alpha x. So if you have that, you pull out e to the power alpha x. This is the formula. Say you have any function of d. You have any function of x. For the sake of simplicity, I took x. You can take any other function if you want to. Oh, sorry, not 3x. General case alpha x. Now what happens? You can bring this out of the d operator. You have e to the power alpha x here. Earlier the function vx was x. You have the same thing here. X. Vx, sorry, Vx. This I don't put fx. Hold on. This is wrong. Hold on. Always the function carries d operator can be denoted by f. Here the function of x is Vx. So here Vx is x. Here you have it in the right hand side. Vx. Now what happens to this? Look, here you have d. Here you have d plus 3. Look at the relationship. Where does this 3 come from? It comes from here. Right? That means it is f of, earlier we had f of d. Now what happens? This is f of d. Now d is replaced by d plus 3, or d plus what? Alpha. Right? So there is another formula. Don't take this down here, but you can, I'll list it here. This usually rarely used, but you can sometimes use it. Now look, what happens is that you can pull out e to the power alpha x, but in the meantime, you have to change the function accordingly. How? D should be replaced by d plus alpha. Okay.